Welcome to MRS Bulletin's Materials News podcast, providing breakthrough news and interviews with researchers on hot topics in materials research. My name is Laura Lay. Have you ever wished you could see a structure rearranging itself as you watch and understand exactly what is driving that behaviour? It sounds pretty exciting, right? And that's precisely what one research collaboration has achieved. At the solid-liquid interface, a two-dimensional network held together by hydrogen bonds can be rearranged by applying an external electric field. Molecules with carboxylic functionalities adsorbed onto the surface of highly oriented pyrolytic graphite have been seen to undergo an immediate and fully reversible transition from an open porous architecture resembling a honeycomb structure to a close-packed morphology when the sample bias of the tip of a scanning electron microscope is altered from negative to positive. Here, adsorption is affected by the surface charge and the STM tip provides a controllable, localized electric field. New research explains why this transition happens. The hydrogen bonding strength, as well as the molecule-to-substrate interactions, were systematically varied. The hydrogen bonding ability was tuned by comparing carboxylates to aldehydes, and a change in the structure was not observed for the aldehyde since the hydrogen bond is comparatively weak. The nature and charge of the substrate was also varied by looking at graphite and graphene deposited onto copper or silica. Experimental results complemented by density functional theory to derive the strength of the interactions showed that the ability of the structure to switch between an open structure to a closed packed one is governed by a synergistic combination of energetic contributions from both the adsorbate and the adsorbate-substrate interactions. Molecular reactive dynamics simulations revealed the switching mechanism. Professor Maggie Lingenfelder from the École Polytechnique Fédérale de Lausanne, or EPFL, in Switzerland, explains.
When you have a system that is in equilibrium, statistically, the proton of one OH will jump into the neighboring oxygen, and then you will have this equilibrium of proton transfer. When you have the proton transfer, this is also the same time the carboxylate group is rotating. So now you are having a very flat molecule with zero dipole moment, but at that moment that you have the proton transfer, the molecule had now a breaking symmetry, and now it has a dipole moment. If I go now with an electric field, which is what I do with the tip, then the molecule does have a dipole moment in that moment, and there I can interact with the field, and then I can induce the switch of the whole structure.
So, you already have a dynamic system where proton transfer takes place as a carboxyl group goes out of plane, inducing a dipole moment for the electric field from the STM tip to act on. This is the key to explaining why structures rearrange in some systems but not in others. The energy at the STM tip is low, less than 1 electron volt, but it's the polarity of the applied electric field that's important. What is fascinating is that by changing just one atom in the adsorbate, in this case replacing the carboxylate with the aldehyde, a small change in the energy of the system results in a huge change to the behavior of the molecular system.
When we went from a carboxylic to the aldehyde, then the whole assembly changes. The fact that the supramolecular interactions, like hydrogen bonded structures, are tuned in such a delicate balance that any little change, so few EVs or few tens of EVs, change completely the system. I always found this fascinating, how a small change in energy gives a totally different outcome.
These findings could have applications in sensors, since clearly recognizable changes can be seen with only a small input. The behavior is known to be reproducible, so could be used to produce reliable chemical sensors. But what's really interesting here is the fundamental science.
I found it very interesting that even for simple systems, there is still so much to learn. This we found totally by chance. It's not something we were designing for the first time. It gives value also to basic research, right? So how important is to explore. We were so excited when we saw the switch that we got into investigating more.
So this exciting behaviour was originally discovered by chance and pursued to uncover the precise mechanism behind it. Calculations and simulations that underpin the results from the laboratory experiments are a major challenge that adds value to the research. This work was published in a recent issue of ACS Nano. My name is Laura Lay from the Materials Research Society. For more news, log on to the MRS Bulletin website at mrsbulletin.org. Follow us on Twitter at MRS Bulletin. Don't miss the next episode of MRS Bulletin Materials News. Subscribe now. Thank you for listening.